I'll remind you from last time we were doing the Laplace transform. Remember what the value of the Laplace transform was for differential equations? We discussed it last time. Here's the Laplace transform. The Laplace transform of a function defined on 0 to infinity, f of t, was just the integral from 0 to infinity, e to the minus st f of t, back to t, right? And this is, we said, like a black box. You've got some space of functions, and somewhere in here, you've got f of t. You throw f of t into this big black box, which is the Laplace transform. Then out comes another space, a space of transforms, a function of s, actually a complex variable, we said. A complex, yeah. So a complex function of a complex variable. And then there's also a map backwards. You can get that from f of s through another, I call it black box because, I just put something in, get something out, and it's not so obvious what's going on. But you get back to f of t using the inverse transform. And this one is the line integral on the complex plane, we said. So we're not going to actually compute any inverse transforms using integration. We're just going to look them up in tables. That's what everybody does until you get into advanced calculus. Okay, so that's what we had. And then these had lots of properties. We had a nice table of transforms for common functions, like Laplace transform of t to the n. Just using integration by parts, we could show that the Laplace transform of 0 was 0, Laplace transform of 1 was 1 over s, and then general Laplace transform of t to the n, including the n equals 0 case is this, is just n factorial over s to the n plus 1. And then the Laplace transform of e to the at was 1 over s minus a. So we could compute all these using mostly integration by parts. Laplace transform of sine omega t, which we were just working on the board for class a little bit, is omega over s squared plus omega squared. Although I think I called this a last time. Let's just use a to be consistent. Sine of at is s squared, a over s squared plus a squared. And the Laplace transform of cosine at is s over s squared plus a squared. And so we memorized these. And then we can use these to solve some differential equations because we also had some theorems, such as the Laplace transform of the derivative of a function under nice conditions was s times the Laplace transform of the original function minus the function at 0. And similarly, you could do higher derivatives. For instance, the Laplace transform of the second derivative of a function, if the second derivative wasn't too bad, was s squared times the Laplace transform minus s times f of 0 minus f prime at 0. All right, so we could use those to solve differential equations. And then we said, for example, let's look at this one here. This is a real simple one, a first order equation that you can solve very easily with the formula for first order equations or separating variables, and probably some other ways too, right? Suppose I, just for an example, suppose I wanted to solve this simple first order differential equation, dy dt plus 2y equals 0. And the Laplace transform, as you can see by this theorem for the derivatives, is really set up not for differential equations alone, but for initial value problems. So I'm going to give the differential equation together with an initial value 1 when t equals 0. So here's my initial condition, y of 0 equals 1, initial value 1, t equals 0. And we'll say, can we solve this with the Laplace transform with a little more work than we did before? And the steps were 3. 1, we take the Laplace transform of both sides. Right? Just to remind you, this is a simple problem, hopefully. And we said, what's not up here, but should be, is the Laplace transform of 0 is 0, because after all, if you integrate 0 from times e to the minus st from 0 to infinity, you still get 0, right? So this side becomes 0. And then the linearity property, which I didn't write down here, but maybe I should. These were the other two properties. I did almost everything. I just left basically this one thing out because I thought maybe I didn't need to, but I think now I should. If I have a Laplace transform of C1 times a function where F1 is a function of t plus C2 F2, this is the linear combinations of the transforms. C1 times the transform of F1 plus C2 times the transform of F2. And similarly, the inverse transform looks like that. If you take the inverse transform of C1 times the transform plus C2 times another transform, it gets you back to C1 F1 plus C2 F2. So that's the linearity property of those things. And so I'll apply that here. The Laplace transform of the linear combination is the linear combination of Laplace transforms. This will Laplace transform of dy dt plus twice the Laplace transform of y. And now one notation we said for Laplace transform is instead of just saying, and sometimes we do just of t just for brevity, we know it's a function of t. And also this could be written as a function of s, so we can have of t and of s. It starts to get too cumbersome. I'll just usually write this. But another notation for the Laplace transform of a function is this f of s, this curly f, script f if you like, which is the notation I was using over here, right? This is C1 times the Laplace transform of little f1 plus C2 times the Laplace transform of little f2. And so we can also use this for the transform of f, which means for the transform of y, we'll write a script y. So this is y of s here. Just changing notation, that's all that is. And what's the Laplace transform of dy dt? Well, we go to the derivative formula. And we say, oh, it's s times the transform of y minus y of 0 by that property there. So this is s times the Laplace transform of, oops, not f, but y this time, minus y of 0. That's transform of the derivative by the derivative theorem. There's the change of notation, and the Laplace transform of 0 is 0 on the right. All right, any questions so far? Does it look good like what we did yesterday? I hope this makes you recall what we did. And this is a very wonderful thing because it takes our differential equation by taking the Laplace transform of each side, turns it into an algebra problem. Now I can plug in what y of 0 is. Y of 0 is equal to 1, right? So I can rewrite this as s y of s minus 1 plus 2 y of s equals 0 by putting in the initial value. And the idea is it takes your differential equation, turns it into an algebra equation, and what's more, if it's a linear differential equation like this, it turns it into a linear algebraic equation, the easiest kind, right? So if I group the like terms, I've got s plus 2 multiplying y of s, right? This term plus this term, minus 1 equals 0. I'll put the 1 on the other side and say that equals 1. Consequently, dividing by s plus 2, I find out that y of s, the transform of the solution, is 1 over s plus 2, right? Y of s means the transform of y, the solution variable. And so now, so that's step 2, I should say. Step 2 is to solve this algebra equation for y of s. And then step 3, we inverse transform. The solution, y of t, is the inverse transform of transform variable y of s, 1 over s plus 2. And now we go over our happy table here and say, what has transform 1 over s plus 2? Oh, that's 1 over s minus a minus 2. So it's e to the minus 2t, right? Put a equal minus 2 in here. So by the table, that's what we said. We won't actually do the integral to calculate these. We'll look these up in the table and hope they're there. This is e to the minus 2t by table. So there's the solution of this problem that I could have gotten very easily with easier with the characteristic equation, right? This is a first order equation with constant coefficients. I'll just check it that way. If I write the characteristic equation for this first order linear DE, I could say, oh, it's R with constant coefficients. R plus 2 equals 0. So it has one solution, R1 equals -2. For a first order equation, the general solution is y equals C1 times y1 of t, where y1 is any single linearly independent function, that is any non-zero function. So this is C1 times e to the R1t, or C1 e to the -2t, is the general solution of this differential equation. And then we apply the initial condition, y of 0 equals 1, tells me that 1 equals C1 e to the 0, tells me that C1 equals 1. And sure enough, check, if C1 equals 1 and y is C1 e to the -2t, we get that y equals 1 e to the -2t. So there's verified by using the constant coefficients method for this first order equation. So it's longer than constant coefficients when you happen to have constant coefficients, but it still has advantages. It will do quite a lot of the linear equations we've already done and some other nonlinear ones in a nice way. You'll see it in the book next time. We'll probably do it on Monday. But you can write this up in transfer function form, and then what you can do is say, well, suppose I had a non-homogeneous equation. This is a homogeneous equation, right? 0 on the right. It's set up that you can put a function in here and get the solution pretty quickly just by inverse transforming, looking up in the table. And then you put a different function in here, look up the inverse transform, put a different function, look up the inverse transform. Kind of an input-output analysis. If I put this into my circuit, that comes out. If I put that, and this thing's going to come out. And so it's nice for engineers to be able to quickly do these things. On top of this, this will solve some problems that we don't have a method for before, but mostly this just solves problems we already know how to do in a particularly nice way for engineering applications. And physics uses it quite a lot too. I'm going to put my eraser. So in some sense, we don't get a whole lot of new problems to solve, but mostly can solve the old one in a nice way that is used a lot in practice. So you go to your engineering book, you're very likely to see this rather than some of the other methods we've been using. All right, so that's the catch up and another example is the first order equation. Now what happens though is when you run into higher order equations, had my trackball this morning, unfortunately. Then more techniques come into play. We saw one last time where I had to use partial fractions to be able to figure out how to do the inverse transform. Remember this one? This is the example we had last time. I'll just put it back up again for a second. Suppose I solve a second order equation. It's already up here, so it won't take long, right? Y double prime plus 3y prime plus 2y equals 0 with two initial conditions. We know it has a unique solution. This y dot means y prime of 0. Sometimes we use dot when it's derivative with respect to t. We said, so the Laplace transform of the second derivative is s squared y of s minus s times y of 0 minus y prime of 0. All right, so that's the second derivative theorem there. Plus 3 times derivative of y, well, the derivative of y is s times y of s minus y of 0. Y of s denoting the transform of y. And plus 2, Laplace transform of y, we write y of s. Once again, we said we grouped, we put in the initial conditions that y of 0 equals 1 and y prime of 0 equals 0. So we put in 0 here and let's see, 1 here for this one, 1s, 0 here and 0 here, and we get this equation. And so now what we get when we take the Laplace transform both sides is a linear equation in y of s. We group the y of s terms, we group the other things, and solve that for y of s by algebra. We add s plus 3 over here and divide through by s squared plus 3s plus 2 and get y of s is this, the transform of the solution. And then we just have to inverse transform that, what we said for a second order equation. Well, I'm not repeating too much, but I really think we need this for today to be able to do the upcoming problems. And this is exactly what's going to be in a lot of your homework. How do I inverse transform this thing? This isn't in the table. And what we said before we slept on it is you can factor this bottom as s plus 2, s plus 1 and say, oh, by partial fractions, a polynomial of lower degree than the denominator over s plus 1, s plus 2 is equal to the number over s plus 1 plus the number of s plus 2. If you run it, use the expand command on your calculator or work tediously and do it by hand, you can find this is the partial fractions decomposition of this quotient, right? And now these are in the table. The inverse transform of the difference is the difference in the inverse transform, the linearity property there. So 2 times the inverse transform of 1 over s plus 1 minus 1 times the inverse transform of 1 over s plus 2. But this is in the table. 1 over s minus a is e to the at. And so this is, right, since you subtract -1 here, this is transform of e to the minus t. This is transform of e to the minus 2t. So our solution here is 2 e to the minus t minus e to the minus 2t to this one. So we did that one also, but we have this trick that a lot of times it's hard to recognize the inverse transform until you do some clever algebra with it. And we want to talk a little bit more about that now. How do you deal with these problems more generally, so we don't have to go to complex line integrals. Here's another theorem that will help us in that endeavor, called the first shifting theorem. Can you see that well enough? Maybe I can make this a little bigger, huh? Sorry if that was a little small. Tell me if you can't read that ever, okay? Especially since I've got this online today. We've got our properties over here at the side we can appeal to. And we'll say, here's the first shifting theorem. There's going to be another one, is what it's called that. And we'll say, if the Laplace transform of f exists for a real part of s bigger than or equal to some number a1, then for and you're multiplying, say then the Laplace transform of e to the at times f of t also exists, right? And it's equal to as you see, f of s minus a. The usual transform of f, but evaluated s minus a, shifted. Now you see why it's called a shifting theorem, right? Imagine s is a real variable, which is not, but here's s versus y. And if I plot y equals f of s, it's got some picture maybe. Y equals f of s. This little Laplace transform of little f. What does f of s minus a look like? I'll put this point s0, y0. Well, with any function, we replace s by s minus number, it just slides it over. So what it does is it goes over to s0 plus a, whatever is subtracted here, and draws exactly the same curve in exactly the same shape. So it shifts the transform along like that. And this is y equals f of s minus a. The transform of y shifted in the s direction. Now again, s is a complex variable, so this is drawing it like it's a real variable, so I'm going to have a number line. But that concept still holds. This is like this, right? If you take the parabola y equals x squared, right? What's the graph of y equals x minus 1 squared? Oh, I know. I just might make x1 greater than x squared, the same number, right? So it's actually the same shape parabola moved over 1 unit. Right, so when you replace x by x minus 1, it slides it over 1 unit, same shape. Same thing with this one. That's why it's called the shifting theorem. Is if you have the transform f of s, then this shifts it along the real axis. There's also a complex axis here, a units, and so it's the name shifting theorem. But this is the big deal here, is that Laplace transform of an exponential e to the at times f of s minus a. It's just the Laplace transform of f of t shifted along a units, at least for real part of s greater than or equal to the sum a plus a1. This is not real important for us. As long as it's true for real part of s greater than some finite number, then we can apply these theorems to solve our differential equations. But just for completeness, since it's a math class, we'll point out that This doesn't necessarily exist for some values of S, right? But there's a half plane way over on the right somewhere for which it's true. All right, so there's the shifting theorem, and now we can use that to solve this next problem. Let's look at this example. Suppose I wanted to solve d squared y dt squared plus 6 dy dt plus 10y equals 0. And again, since this is defined or set up for initial value problems, let's put some initial values with it. Y of 0 equals 0, and y prime of 0 equals 1, just to get some real easy numbers so we don't get a hard bunch of numbers slowing us down here. So there's an interesting problem. This one we can also solve right with constant coefficients, right? Just write the characteristic equation r squared plus 6r plus 10 equals 0 and plug in the initial conditions, and it works. But let's try it by the Laplace transform this time. If I take the Laplace transform of the left, what do I get? So 1, I take L of each side. L of each side. I'll write this in brevity now. What's the Laplace transform of the second derivative? For the theorem, right, it's s squared times the transform of y minus s times y at 0 minus y prime of 0. There's the transform of the second derivative, right? Plus 6 times the transform of y prime plus 10 times the transform of y equals transform of 0 is 0. So there's the transform of the equation. It's 1, 2, 3. Transform the equation, solve the algebra problem, inverse transform. That's what you do on every one of these, right? So, well, let's see. Y of 0 was equal to 0 nicely. So this becomes 0. Y prime of 0 is 1. And over here, I forgot to put in this stuff. S, y of s minus y of 0 is the transform of the derivative by this one. Just using y instead of f. And the Laplace transform of y, we just call that y of s. And now let's see, y of 0 is equal to 0, so this is also 0. So what we've got is just 0, 0, and minus 1 for the initial conditions. And so we'll say this is equivalently grouping all the y of s terms together. S squared multiplies y of s. 6s multiplies y of s. And 10 multiplies y of s. Look like the characteristic equation, r squared plus 6r plus 10 equals 0. So we're getting these same numbers in the same ways in here. And then I've got minus 1 equals 0. I'll add 1 to each side and get equals 1. So this is just by algebra. That's our step 2. So if you start combining these steps quickly, you can do it. Here I did the transform in one step. Here I'm doing the algebra in one step. But I say get used to doing these, they're not so long. And now let's see, we've got, I guess I've got one more step. This is going to be 2 steps, I guess. Y of s equals 1 over s squared plus 6s plus 10. And so I have to take the inverse transform of this one. How do I take the inverse transform of this one? Oh, partial fractions, right? I could use partial fractions on this. Uh-oh, not so. Why can't I use partial fractions on this? Technically I can, but not within the math we know in this class.
It doesn't factor.
Yeah, it doesn't factor anymore with the real is excellent. Yeah, if you compute, this is as squared plus bs plus c, all this a, b, c. B squared minus 4ac is, let's see, 36 minus 4 times 1 times 10 is negative 4. When this is less than 0, this is called an irreducible quadratic because it doesn't factor over the real numbers. You can factor with complex numbers, but you can't factor over the real numbers. So I can't use partial fractions with real numbers. I have to use partial fractions with complex numbers. Then I've got to integrate complex valued functions, which we don't know how to do yet in this class, and so it's a mess. So the way it's normally done is instead with the first shifting theorem. When you get a reducible quadratic, you reduce it using partial fractions, like we did in the last example. If you get an irreducible quadratic here, then you use the shifting theorem here. So what I'm going to do is shift this along, if you will. So I'll say y of s is equal to that, and I won't try to factor it. I'll instead say this is 1 over s squared plus 6s, and say, what do I have to add to make a perfect square in here? Well, to make a perfect square, you take 1/2 of 6, is 3, and square it, and you get 9. That's what has to be in here to make this a perfect square. Put it 9. Now this will be s plus 3 squared, right? It's s plus this number, I squared. And then s squared plus 6s plus 9, oh, plus 1 makes 10. So now there's the same denominator. Y of s is equal to this. And I'll write it more suggestively. This is 1 over s plus 3 squared plus 1. Get rid of this, I guess. So there it is, the transform of the solution in step 2. I said one step, I was a little off. it's 1 over s plus 3 squared plus 1 by completing the square this time, since I have an irreducible quadratic here. How do I inverse transform that? Step 3 says that the solution y of t is the inverse transform of this. L inverse of 1 over s plus 3 squared plus 1. And this is kind of tricky because it's backwards thinking. You ever try to do backwards thinking, you know, like try and spell supercalifragilisticexpialidocious backwards or something? You can't do it. I mean, it takes a lot of practice. So same thing happens here. It takes a little practice, right? What you have to do is say first, oh, if it was 1 over s squared plus 1, I'd know what it was immediately, right? It would come out of, it would be the inverse transform of sine t, right? A equals 1 over here. 1 over s squared plus 1 would give me sine at when I inverse transform, go from here back to here in the table. Alas, but I've got that stupid s plus 3 sticking in there. What am I going to do with that? I know what to do with that. Inverse transform, or the shifting theorem says e to the at f of t is equal to f of s minus a. If I think of this as s minus a negative 3, I could say this thing in here is the transform of e to the minus 3t times the inverse transform of 1 over s squared plus 1. The transform I would get, so implicit with this goes that this implies then that the inverse transform of f at s minus a, this is the backwards thinking right here, must therefore be e to the at f of t. And so that's what I'm writing here. If I have s minus a negative 3, I get e to the negative 3t times the function that whose transform is this without the shift. So I have to inverse transform 1 over s squared plus 1 instead of 1 over s plus 3 squared plus 1. And now I know what that is. That's in the table. That's a equals 1 in the sine transform. So this is e to the minus 3t sine t, sine 1t if you like. But look at that, Murphy's law didn't get me for a change. I actually fit that on without running off these. Okay, any questions on that one? Does that make sense? So here's what you have to do on the problems this weekend when you try them. And come back and bring me questions. Again, I'll remind you, on Monday we have an extra credit problem for 5 points. It won't be on this stuff. It'll be on the mechanical vibrations or the electronic circuit, the damp-driven oscillator, I guess what you call it. So I'll give you a damp-driven oscillator problem on Monday. And then, however, this will be definitely on the final. This will be one of the major topics on the final. All right, so there's the shifting theorem, and now we know how to solve second order equations pretty generally there, because if we start with a second order equation, we'll get, oh, I was going to say one more thing, we'll get a second order polynomial at the bottom here. We can either partial fractions or use partial fractions or completing the square. The problem comes in, see if I can copy this back down again, now that I really should erase that y double prime plus 6y prime plus 10y equals 0. This is great for homogeneous equations, right? 0 on the right comes out like this. But what if it's non-homogeneous? What if I put an f of t over here? Now I've got a non-homogeneous problem. When I take the transform, I get this with an f of s. Transform of this one. And so now it may not be a simple matter of just using partial fractions or completing the square. What happens in a lot of practical situations, though, this happens in electronics engineering a lot. A lot of times in electronics engineering, this actually comes out to be a polynomial. You get input-output systems and so forth. This will be a polynomial on top, not just electronics engineering, systems analysis and so forth, like control systems engineering. They'll get polynomial over polynomial. And what you can do is do polynomial division and make this a polynomial plus or make this a partial fractions problem still eventually. And so sometimes that still works, but even more generally, sometimes it's not so simple if this right-hand side isn't something that's pretty elementary function. But I just want to point out, now you see where that transfer function thing comes in. The book mentions these two, is if you've already solved this homogeneous problem, you can try putting in different functions and maybe using some of the same analysis over and over to evaluate each of these things for different input functions. All right, so there's we've talked too long again, of course. Good. So why are we studying this thing is the question. If we're just solving all these problems we already could do before. Well, here's the big reason why we study Laplace transforms. There are some new problems we can do, and they have to do with functions that are not satisfying the criteria we had before. So why study DE solutions by Laplace transform? When we're just saying, well, we could solve a lot of these problems by our previous method. One reason is that for linear equations, linear DEs, and by the way, this applies to higher order differential equations. We're only doing second order because it brings in all the interesting things you need to see, but this works for higher order equations too. You've got higher order polynomials in the denominator, and you have to, factor them and stuff, and use partial fractions that are longer. Okay, one reason is that linear DEs with f of right-hand side of RHS, f of t not continuous. Or not continuous, and sometimes not even differentiable. Not even finite. At points, at a finite number of points. Can sometimes be solved by this method. Where they couldn't before. Our theorem said if on the right-hand side f of t is continuous, then this is the nice classical solution, a function that has a derivative at each point, and they're equal along this interval. But the fact is, these sometimes you get non-continuous functions on the right. Like here's an engineer putting into a circuit of some sort. Here's your LRC circuit again: a inductor, a capacitor, and a resistor. And we said we could put an impressed voltage on here, right? Some sort. Maybe it's this alternating current or alternating voltage here. What happens, however, if I maybe have nothing here, and all of a sudden I just instantly attach a battery? how do we model that? We could say that we could model that as an instantaneous change in the voltage. So on the right-hand side, we have a function that jumps from 0 voltage to a positive voltage. It's not true that it jumps instantaneously, but you know, for all modeling purposes, it's so quick, we'll just have to model that way. We don't know how else to do it really. And so what you can do is say, if I suddenly attach a battery and model it as instantaneous, the old method doesn't work because the battery function where there's a sudden jump in voltage, the right-hand side function in an LRC circuit problem, has a discontinuity, and our old methods don't work, but Laplace transform does work so for that. So for this purpose, we consider some non-continuous functions and some that aren't even finite. We're just going to do 2 of them really. But they're really useful for engineering purposes. It's not just that, it's like, if you have a cue ball on the table, you want to model that and you strike it with the cue stick. How do you model that? Well, it's hard to say, well, it goes up with this function and gradually gets up. You can normally just model it as an impulse, a sudden jump in momentum of the ball. And you know, then it's a discontinuous model, even though in fact it's technically continuous. And if you did it in slow, you know, it's too hard to figure out how to model that as anything but a quick discontinuity. So we consider first the Heaviside unit step function, which is a unit jump in a function. And unfortunately, in the notes and in the book, we use different letters, but it's the same thing, right? So in the notes, I say h of t is equal to 1 for t greater than or equal to 0, and it's equal to 0 for t less than 0. That'll be the Heaviside step function. Well, it's a unit step function, so another good notation is what the book uses, u of t. So u of t and h of t will mean the same thing. H for Heaviside if you're this fan or something, and u of t if you can remember unit, right? And so it has this nice graph like this. What does it look like? T versus y equals h of t. It's equal to 0 along here, and then at t equals 0, it jumps up to 1. So it's a unit step from 0 to 1, right? This is y equals h of t, the unit step function. Well, what if we're not going to make a jump at 0? But the idea is here I attach a battery at time 0 and it jumps from 0 voltage up to 1 is the idea. Or when I was working at the FAA, we had an interesting problem where planes coming down to land, and we used this in the model actually, modeled by actually a former World War II German who came over to Britain. Like we took, oh, geez, look at my name here. But we took some of the German scientists over here, and one of their German scientists at the end of World War II was Pinsker, and what he came up with was this model of the airplane's coming down, and the pilot suddenly realizes, oh, I'm too low, and pulls the stick back, and how do you model that? The pilot suddenly going from straight ahead to flaps full up, and trying to make what they call a missed approach, right? You know, it's some problem has to make a missed approach. Well, you just model the lift is jumping from 0 to suddenly up here, and so it comes up in mechanical situations as well as electronic situations. That was the point of that. So we solved that model and looked through Pinsker's model and adjusted it a little bit for the model we were doing. Kind of a neat story though. I knew one of the RAF pilots who told me all this. He's the guy who got this model from Pinsker. Anyway, what is the Laplace transform of this? We're going to apply a Laplace transform where the right-hand side, the forcing function, has a discontinuity in it. We can't use our old methods anymore. instead we'll use the Laplace transform. And so what's the Laplace transform of the Heaviside step function? I wonder. Well, let's see. I know it's by definition, it's the integral from 0 to infinity. I don't want to do this yet. I want to first, one more thing. I'm sorry. This will, also, what we really need is, if you attach the battery to 0, you can say, well, my model starts at 0, so I can just model this over the battery is there the whole time. But what's interesting is this battery is suddenly attached at t equals 1 or 2 after I've started the model. We have, by shifting again, we mentioned shifting functions, that what is h of t minus 2, or let's say h of t minus t0 in general, is equal to then 1 for t greater than or equal to t0, and 0 for t less than t0. Right? And so here's t, and here's y. If I plot y equals h of t minus t0, it's 0 until this time t0, and then it's equal to 1 after that. So it's a unit step at t0, right? Because this is, if you plug if you just add t0 to whatever you here, whatever you had there, you get this one. And so there's the shifted function. And what is the Laplace transform of this is what we're really interested in. It also applies to lots of other things. I have one problem in the text there where you've got this mass on a spring. Here's my spring, right? And it's going along, and then all of a sudden I set another weight on it, right? Oh, we can treat that as an instantaneous change in the mass or something, or an instantaneous force is what we can do more easily. There's an instantaneously additional constant force by the weight of the mass that I put on top of the old one, part way into the problem. I set another mass on there. So you can model things like that too. Whenever you make something that can be modeled as an instantaneous change. All right, so what's the Laplace transform now most generally of h of t minus t naught? Well, that's the integral from 0 to infinity of e to the minus st, h of t minus t naught, dt. Oh boy, how am I going to do that one? Do you see it? Maybe. Oh, I know what it is. H of t minus t naught is equal to 1 after t naught and 0 before. So I could just say this is the integral from t naught to infinity. Or let's write it two things, just to make it crystal clear. This is the integral from 0 to t naught of this. Plus the integral from t naught to infinity. Well, when you're between 0 and t naught, h of t minus t naught is 0. So this is integrating 0, and you just get nothing out of that. And this one is equal to 1. So you can rewrite that this is actually the integral from t naught out to infinity of e to the minus st times 1 dt. There it is. It's just that integral. So what is that one? Well, we know how to do that, right? The integral of e to the kt is 1 over k e to the kt. So this is minus 1 over s e to the minus st, going from t0 to infinity, where the infinity means go from t0 to b and let b go to infinity. So this is minus 1 over s e to the minus infinity effectively is 0. Let's just write that down. 0 at the top endpoint, because this one overpowers the 1 over s. And then minus at the bottom endpoint, minus 1 over s e to the minus st0, plugging in the bottom endpoint. So what it is apparently, what we've proven is the following theorem. We'll say hence, the theorem for the Laplace transform of the unit step function at t naught, and sometimes they'll call this, well, never mind, let's leave that off. The theorem says that the Laplace transform of h shifted by t naught is equal to 1 over s e to the minus s t naught. So there's there's that, you know. Here's my picture on the board here again. Here's h of t is a unit jump at t equals 0. This is probably better I can draw. Here's the h of t minus t naught is a shifted over t naught units. And we call this the second shifting theorem. I should have written that up there. If this way this works, I don't have my trackball that is okay. And there's the theorem. More generally. So I proved this for the Laplace transform of h of t minus t naught. But with a little more work, we can more generally show, and the proof is here. I'll just go through it on the board. So more generally, we similarly show by breaking up into two pieces like that. We can do the proof of this one if you want, that for f of t with transform f of s, the second shifting theorem difference is that this one is going to shift t instead of shift s, so it's shifting the t coordinate, which is a real variable. Second shifting theorem if f of t has transform f of s for real part of s for an integral of some number a. Then the transform of h of t minus a, f of t minus a, so they're both shifted, is equal to e to the minus st naught f of s. Well, this is the transform of f of t, not f of t minus a. I'm sorry, this is t naught here. I'll use the same letter. So if a function is shifted multiplied by the shifted Heaviside unit step function, then it has this transform. So this one's called the second shifting theorem, and it says the inverse transform of this is shifted function f multiplied by 0 for t less than t naught. So I put a real basic example in the notes that I really like. I think it really exemplifies as well. See what you think. And here's the proof. You want to see the proof just real quick. Laplace transform of h times a function that has a Laplace transform. You just do the same thing we did there. Is integral e to minus st times that. And then you break it up in two parts from 0 to t naught to infinity, just like we did when we had 1 in here instead of the general f. And the first integral is integral of 0 because the Heaviside step function is 0 on this interval, just like over there. And on the second interval, we can make a u substitution, u equals t minus t naught. Oh, I'm sorry. Here I just since it goes from t naught to infinity, and this is 1 there, you just replace this with 1. The second integral is replaced with 1. First integral is replaced with 0. And then since this is integral of 0, it's just 0. And then this one, if you now make the substitution, let t hat equal t minus t naught, then this becomes e to the minus s t hat plus t naught. F of t hat replaces that. From 0 to infinity, it changes the interval. And now what is this? If you pull the minus st, e to the minus st naught out, it becomes integral e to the minus st hat, f of t hat. And that's just the Laplace transform of the f without a shift. And so that we get e to the minus st naught f of s. So that's the proof of the theorem there. I'll just do that real quickly and say, here's a real nice example then that I like. Here's a shifted parabola, such as the one I showed you a little bit ago. And suppose I want to take the transform, so first sketch this function f of t, which is a shifted half parabola. It's h of t minus 1 times t minus 1 squared. All right. Yeah. Okay. And find its Laplace transform. Wonder what that is. Here's how you do the sketch. You say f of t, or y equals t squared, had a graph that we're very familiar with from maybe middle school or something. Y equals t squared, t, y, and goes through these wonderful points, 1, 1, minus 1, 1, 0, 0, basic Bezier parabola. So what does y equals t minus 1 squared look like? It just shifts it over 1 unit, because now t has to be 1 greater to square the same number, so it goes through 1 here. Here's y equals t minus 1 squared. It's exactly the same shape, just moved over 1 unit. We just, for each 1 greater, I get the same parabola. And now I've got, just add 1 to every t coordinate, 1, 0, 2, 1, 0, 1, right? And that's y equals t minus 1 squared. Oh, but what happens when I multiply by h of t minus 1? That's equal to 0 for t less than 1, and 1 for t greater than or equal to 1. And so it just cuts off the left half of the parabola, multiplies this part for t less than 1 by 0, and you get a half parabola. So, and it's 0 down here. So this is the final graph. It's 0 here because you multiply it by 0. And beginning at t equals 1, you get 1 times this function. It's just this function back. So you get this half parabola. There it is. Y equals h of t minus 1 t times t minus 1 squared. Looks like that. And now what's the transform of this function? This might be an engineer who goes along with 0, applies voltage, and then applies a parabolically increasing voltage. How do you put that into your circuit? You know, if that's your forcing term on the right-hand side in your LRC circuit, then you want to be able to solve it with a Laplace transform, let's say. And your old methods, actually, I guess they could apply to this because this is actually a continuous function and would guarantee unique solution and all that. But, you know, you could also do this if you made a jump here, and this method would work. Plus, you have a problem breaking that old problem up into 2 pieces. The old methods don't tend to work when you have a piecewise defined function like that. Plus, the other advantage is you can use it for piecewise defined functions. It would be hard with the other methods. All right, so so there's that one. Now, what's the Laplace transform of f of t? Well, by the second shifting theorem, since it's the Laplace transform of h of t minus 1, t minus 1 squared. By the second shifting theorem, this is e to the minus st0, where t0 is this number. So it's e to the minus s times 1 times the transform of the function without the shift, f of t, L of t squared. Right? So this is f of t minus 1. This is f of t. That's what the theorem says. Transform of h, shifted h, shifted f is e to the minus st0 times the transform of the unshifted function. What's the transform of t squared? Remember that very well, right? This is t to the 2. Laplace transform of t to the 2, right, is 2 factorial over s to the 2 plus 1 is 2 over s cubed. So I can do that one. So this will be e to the minus 2e to the minus f over s cubed. There we go. This more exotic function has a real nice, easy Laplace transform, and now I can do all those difficult problems that I couldn't do before. Comments on that one? But here's the kind of thing sometimes you get again in certain engineering applications, right? You might have a piecewise defined function here where f of t is equal to 0 for t less than 1, and it's 1 for t between 1 and 2, then it's 0 for t greater than 2. How do we take the transform of that? If you have, this is a discontinuous function, and I need to make a note at this point also. Engineers know that in the things they model, they're not really discontinuous. For math diagram versus a engineering diagram, it'll be a little different, the picture sometime. Here's the Heaviside step function for us. Here's maybe h of t minus t0. We said that's what we're actually using mathematically, right? This is y equals h of t minus t naught, let's say. But the engineer won't draw it like that. The engineer will draw it out here like that, because in reality, it just jumps up quickly, and so the engineer will draw a continuous function like that. In this problem, we'll similarly do the following. They call this a square wave. You're inputting a sudden blip, a signal into a sending out over the radio or something. So suppose I have this function, f of t, as we said there, is equal to 0 for t less than 1. It's equal to 1 for 1 less than or equal to t less than 2. And it's equal to 0 again for t greater than 2. If you try and sketch that, it looks like this. It's 0 till t equals 1. Then it jumps up at t to y equals 1, when t equals 1, and then it jumps back down over here. And so the engineering diagram looks like this. 1, 2, 1. And you call it a square wave. Anyway, because we got a square here, square wave, even though you didn't close the bottom. All right, if you think of this as 0 not being here or something. Anyway, so there's a square wave. What is the transform of the square wave? Well, we can do that quite easily too, right? Maybe we should just do it off of there, huh? One way engineers sometimes do this, and other people too. Like I say, physicists use this a lot, and people in other things. Whenever you have a discontinuity in here, it's just they have more discontinuities when they turn things on and off, right? Find Laplace transform f of s in this function, right? So we'll say f of s, first we'll say f of t can be modeled for the square wave as h of t minus 1, so that you get a unit jump at t equals 1, minus h of t minus 2, so you jump back down to 0. So for t greater than or equal to 1, it's going to be 1 minus 0, t between 1 and 2, but when t is greater than or equal to 2, it's 1 minus 1, and when t is less than 1, it's 0 minus 0. So that is another way of writing this piecewise defined function. You can rewrite it in terms of unit step functions, and in the book again, they'll put u of t minus 1 minus u of t minus 2, right? Or in some books, I started to say this earlier and I skipped over. Someone will put u1 of t minus u2 of t, and they'll put the shift down here. And so there's different notations, unfortunately, different books. So let's not even go there, but I wanted to mention that sometime. All right, so what's the transform? We can say that this is f of s is the transform of the difference. Well, the transform of the difference is the difference of the transform. It's the Laplace transform of h of t minus 1 minus Laplace transform of h of t minus 2, right? But we know what the Laplace transform of the Heaviside step function is, right? It's 1 over s times e to the minus st0, where this is t0. So it's e to the minus 1 t0 over s for this one. And this one is e to the minus 2 t0 over s. And it's as simple as that. How about that? So when you get these discontinuities, never fear, it's not hard to take the Laplace transform and figure out what their transform is. And then you can try and inverse transform these with some theorems that are coming up. That's what's usually done rather than trying to make hard integrals out of these. You look them up, do this, so you can look up everything in tables. So here's a differential equation I put in just for fun. Or use the Heaviside step function. Oh boy. Looking at the time. T squared u dt squared minus 9u equals h of t minus 2. You turned on something at t equals 2 and you need to jump. But together with, since it's a Laplace transform problem, we'll put in two initial conditions for the second order problem. U of 0 equals 0 and u prime of 0 equals 1. That's some real simple conditions. Solved by the Laplace transform method, since we've got a discontinuity, so all methods don't work, right? So we're going to take the Laplace transform of the left side, take L of both sides, and the Laplace transform of the second derivative is s squared u of s, if I use u for the variable, minus s u of 0 minus u prime of 0. The second derivative theorem. Then minus 9 transform of u is just u of s equals h of t minus 2. We know its transform is e to the minus 2s e to, put t0 here. This should have been s. No, I'm sorry. No, let's go ahead. E to the minus 2 t0 over s. The Laplace transform of h of t minus 2. And so now, let's say u prime of 0 is 1, and u of 0 is 0, so that goes away. And so we write equivalently in step 2, how do we solve this algebraically? We said it's s squared minus 9 times u of s. Again, it reminds you of the characteristic equation for the left-hand side, r squared minus 9, s squared minus 9, right? Equals, well, I've got to add this 1 over here, right? This is equal to 1 plus e to the minus 2 t naught over s. There it is. And so that's algebraically grouping the u of s terms and the other terms. And now we divide by s squared minus 9 and write that u of s must be 1 over s squared minus 9 plus e to the minus 2 t0 1 over s times s squared minus 9. And so we've got that one. I think it's on the next page, is it? Yeah. But the idea is you're able to solve now. There we go. Yeah, so that looks all right so far. And now I want to inverse transform it. So what I'm going to do is expand this, and this is where we hate to do these partial fractions by hand. Once you start to get past quadratics, it gets complicated. How does this factor 1 over s squared minus 9 factors as 1 over, let's see.
It should be s plus 9, s minus 9, but I think they just blurred through the partial fractions.
Yeah, this is partial fraction here.
Yeah.
Yeah, this is my example. I ran it in the calculator, so hopefully it's correct. If it's not, let me know. But the partial fractions, 1 over s squared minus 9 is 1 over 6s minus 3 minus 1 over 6x plus 3. partial fractions of 1 over s times s squared minus 9, that's harder, right? So, but partial fractions on the calculator says it's 1 over 18 s minus 3 plus 1 over 18 s plus 3 minus 1 over 9s is the partial fractions to this, and then it's all multiplied by e to the minus 2s. So this is why I have the notes up, is so I don't have to spend 10 minutes doing it on my calculator in class or by hand, even worse. So let's see, we're over here. So this is actually equal to my partial fractions. And the trouble comes in is that sometimes these things in the denominator are irreducible and some of them are partial fractions, and you can have like fourth or fifth order denominators and have a whole slew of terms here for partial fractions. So partial fraction says that this one is actually 1 over 6, s minus 3 first, yeah, s minus 3 minus 1 over 6, s plus 3, that's how that one decomposes. And then plus e to the minus 2s minus 2s over 18s minus 3 plus e to the minus 2s over 18s plus 3 minus 1 over 9, was it? S e to the minus 2s. Okay, so there's the transform of the solution. Now we just have to inverse transform each of those terms. Fortunately, and for us, we know exactly how to do every one of those. What's the inverse transform of 1 over s minus a? It's e to the at. So this is e to the 3t times a sixth. 1/6 e to the 3t. This is by table. All right. Laplace transform of 1 of e to the at is 1 over s minus a. So you have to memorize at least that many tables. It takes too long to go, oh yeah, that is in the table. Right? So 1 over s minus 3 is the transform of e to the 3t. 1 over s plus 3 is e to the minus 3t. And those are easy. Now, what about these? I've got 1/18. What's the inverse transform of e to the minus 2s over s minus 3? What's the transform? What is that the transform of? We go back to the first shifting theorem. To get an e to the minus 2s, that's e to the at. E to the at times the inverse transform of what's left. No, I'm getting this wrong. This is a shift. You shift 2 units. It's h of t minus 2. Sorry. H of t minus.
I don't think that's a shift.
Yeah, I'm messing it up here. What am I doing wrong?
Wouldn't it just be 11?
Yeah, it's h of t minus 2. Say again?
No, you're good.
Okay, yeah, it is. It's h of t minus 2. Of the shifting theorem. The transform of what's left without the shift, or with a shift. You notice that 1 over s minus 3 is the transform of e to the 3t, but we have to shift this function. So it says e to the 3, not t, but t minus 2. It's the inverse transform of inverse transform 1 over s plus 3 is e to the minus 3. It's e to the minus 3, I should put here. E to the minus 3t. The inverse transform of e to the minus 2s over s plus 3 is h of t minus 2, e to the minus 3 shifted 2 units, e to the minus 3t minus. So this is the second shifting theorem, or the shifting theorem. Table, followed by shifting theorem. So like I say, you have to practice these, shifting theorem. And now you've got this one, and then similarly, the last one here is 1/18. Yeah, this one is e to the plus 3t, I'm sorry. Because it's s minus a e to the at. And this one is e to the minus 3t, e to the 1/18 h of t minus 2 e to the minus 3t minus 2. That's this one. And then this one, 1 over s is the transform of 1, but the e to the minus 2s over s is the transform of h of t minus 2. So this is plus minus 1/9 h of t minus 2. That's the inverse transform of e to the minus 2s over s, we recall. There we go. So there's the solution to this problem. If you take some sort of device that has this homogeneous equation, but then you put a unit forcing function, if you on the right side. I call it a forcing function because if you put the mass here for a unit mass, if this is a mass here, this would be the force applied at would jump in 1 unit. Let's see. Yeah, so this is equivalent. This is the force here. If this is mass times acceleration here, and then you can think of this as like the mass of the spring or something. For a spring, it would be a plus 9u. All right, so there's how you can deal with this problem, and then it has a nice graph. I wish I had a little more time today. There was one more function I wanted to do, but maybe I'm trying to do too much. Huh? On Monday, we'll do the Dirac delta function. Paul Dirac came with Einstein and those people. We can do that next time, but. Let's see if I don't have the graph of this one, do I? Thought I did. Well, I wanted to point out, I guess I'll point it out next time. You can get so-called solutions to differential equations if you put something more exotic than this Heaviside step function, where the solution actually doesn't have a derivative at some point. It's got a kink. What this is this is the function that satisfies the derivative at each point, except at this one point where you give it a unit impulse. We'll talk about impulse next time. It's change in momentum at t equals 3. And so it's the unique function that satisfies the derivative everywhere, but has this so many unit impulse at this point. Like you hit the cue ball or something at that time. All right, so let's, I think I gave you all the problems out of there last time. Now we can do, I'll give you these problems and don't do the ones that have the Dirac delta function. And if you see this in there, don't do it. Just use the ones with the unit step function u. 3.4.3, 1 and 3. If you want, you can go ahead and look ahead at the other ones. I wish we could have finished the rest of them today, but let's do those for Monday. Plus finish the ones you've already started on last time. Yeah.